Hello everyone. Now we're going to do an example where we have a titration calculation, and you're going to determine a concentration of an unknown acid, and then also be able to propagate the uncertainty involved in that too, so that you have an associated uncertainty with your unknown acid concentration, right? So just to review, just so we remember what we just did in the last video, right? I need to get back onto the PowerPoint here. There we go. And so we talked about the difference between relative uncertainty and absolute uncertainty in molarity, right? And I discussed how we can interchange between those equations. And so if you need to look at that, look at part one, just to remind yourself. And then we went through a simple molarity calculation where, and again, my head's blocking it. I apologize. Let me move my head out the way. There we go. And we went through a simple molarity calculation from massing out a certain amount of sodium chloride and dissolving it in some water, and then we calculated the associated uncertainty involved in that process, right? And so now we're going to go through and do it with calculations and values collected from a titration. I almost said balance, but from a titration. Okay, so a very similar thing, right? Very similar thing. The key here is that whenever you're doing propagation of uncertainty from molarity, is that you always have to. The first thing you always have to do is not convert. Sorry, you have to determine the uncertainty for the formula weight, right, of the molecules that you are working with. Okay, or the compound you're working with. So, in this problem, you're doing an acid-base titration, right? And then this calculation here, or this particular example here, will also help you with your calculations and propagation of uncertainty in your lab reports too, for the titration you did last week, or not last week, but on Wednesday. So you're doing acid-base titration, okay, and you're titrating 25.500 plus or minus, and again I'm going to try to write it the way the book writes it, 0.5 mils of acetic acid. I'm sorry, not acetic acid, of hydrochloric acid of unknown concentration. Right, of unknown concentration. So this uncertainty here comes from the fact that you used a graduated cylinder. Cylinder? Cylinder. Okay. Use a graduated cylinder. And I know that in my previous example over here, I said that graduate cylinders have a plus or minus 2 mil. That's for the example that was given here was for a 250 milliliter graduate cylinder. So for this example, you actually are using a 50 mil graduated cylinder, right? And its uncertainty, like I said, is 0.5 mils. Okay. So this is uncertainty you'll use. So for example, back in the previous lab, or previous example, the uncertainty we used here was with the balance, and the balance was 0.002, right? Well, here it's going to be 0.5 for the graduate cylinder that you use to volume out, measure out the 25 mils of unknown concentration hydrochloric acid that you're putting into your flask, right? So you do this with you titrate titrated with 0.166. Sorry, I wrote that number wrong. I need to make sure my numbers are right here. you titrate with 0.16266 molar in AOH, right? And notice that there's not an uncertainty associated with that, so you're going to have to figure that out, and we'll get to that in a second, right? And on your burette, you had a final volume of maybe I should just write it the other way. I'll do the initial volume first, that way you have to actually do the calculation correctly. And when you titrated with it, you had an initial volume of, what was your initial volume? You had an initial volume of 15.00 mils, and you had a final volume of 25.00 mils. Okay, and then this was done, of course, using a burette. And we learned already in lab that a burette has an uncertainty, a 50 milliliter burette has an uncertainty of plus or minus 0.05 mils. Right? That's its uncertainty. Okay, so the question then is, right, what is the concentration of the unknown acid and its associated uncertainty? So again, just like the last example, we're going to have to figure out the uncertainty that's associated with the formula weights for each compound first, right? And if you didn't already know, for every titration, or for that matter, any reaction you do, you always have to write out a balanced chemical equation. So let's just do that, just so that we know what our balanced chemical equation is, and we know that this is since it's sodium hydroxide and hydrochloric acid, it's a 1-to-1 molar ratio, right? So it should be HCl aqueous NaOH aqueous becomes H2O liquid plus NaCl aqueous. Right, we always come back to Cl, right? We always come back to Cl. And notice there is a 1-to-1 molar ratio between the HCl and the sodium hydroxide, right? Both those have ones right there, right? If it's blank, it's got a 1. So that's great. So let's go through. We're going to have to figure out the associated uncertainty with this formula weight and this formula weight first. Okay, so we'll do sodium hydroxide first. So sodium, oxygen, and hydrogen, like so, right? And we got sodium from before. That was easy. 22.9. I take that back. It was easy to find, but it's hard to write because it's super long. 22.897692.8 plus or minus. Again, this is the long one. 0.0000002 grams per mole. Then oxygens is, when you look it up into in the chart or the periodic table that we have in our textbook, right? It's going to be 15.9994, and its uncertainty from our textbook's periodic table or our chart that I provided you is 0.0003. grams per mole. And then hydrogens is a little easier, 1.00794 plus or minus 0.00007. 4 zeros correct? Yes. Grams per mole. Yeah, it's always hard again, like I said, to keep track of my zeros. I have a lot of zeros, right? Okay, so we'll do that, right? And we'll do what we did in the last one. Again, just to recall, these are the uncertainties associated with the formula weights, right? And so we'll do sodium hydroxide first. And so simple simple arithmetic here. So addition operation. 22.8989 blah 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 plus 15.994 plus 1.00794. All added up together is 39.9971009. And we won't round or anything yet until we figure out what our uncertainty is. And when we do that uncertainty, this is an addition operation to get this value. So we'll use the normal addition equation for absolute uncertainties, which is this. And then again, I'll just abbreviate this by, not abbreviate this, but write this in scientific notation so it's shorter. Don't have to make the thing so long. Plus, so 2.0 times 10 to the negative 8 plus squared plus the 0.000, 3 zeros, yes, 3 squared plus the 0.00007 squared. Okay, like so. And then we can go through and calculate all that out, and what you should get is plus or minus 0.003. Cool. All right, and so this goes up to 3 decimal points here for the first uncertainty. So we'll do the same thing for here. We'll cross all those out, and since the number is 1, we get 39.337 as our molecular weight for sodium hydroxide, right? So again, don't forget to put that in parentheses so it looks like in the book, and then your unit is grams per mole. And I may have forgotten to put that on the previous one too. You can blame me for that later. No, I wrote it there. See, right here. I didn't forget, so you can't forget either. Okay, so there we go. We'll do the same thing now for hydrochloric acid, which is a little bit easier, right? We have hydrogen, which we already have, and we have chlorine, which we actually have from the previous example. So hydrogen is 1.00794. Chlorine is 453. There we go. And then again, plus or minuses here. For hydrogens, it was 0.00007 grams per mole. And then for chlorine, I've already forgotten. Let me look back. Yes, it is. There it is. It's 0.002 grams per mole. Right? So, same calculation again. Easy arithmetic. Just so that everybody's clear, this is the uncertainty for the formula weight. Or the formula weight. Right? So you add that together and you get 36 point. I ran out of room here. I need to make it smaller here. No, it's probably fine. 36.46094. We'll round it off after we get done with our calculation of the uncertainty. This one is a little bit shorter and easier. The square root of 0.00007. Make sure you keep track of your zeros. Squared plus the square root, plus the square of 0.003. All right, square root all that. And so what you should get is plus or minus plus or minus 0.002. Okay, 0, 2. So 3 digits there, so 3 digits here. So we just report this as 36.461, right? 36.461. 9 rounds to 0 up to 1. So that's good. That's our first step, right? The next thing you should probably do too is do the volume calculation, right? So the VT for the NaOH equals the VF for the NaOH minus the VI for the NaOH, right? So that equals then 25.00 mils minus the 15.00 mils, right? And so that equals 10.00 mils, right? Cool. And then we have to figure out what the uncertainty is, which is pretty simple because this is just a regular old subtraction. So the uncertainty for this equation, the SY, equals the square root of, what was the uncertainty for the B red again? Right here, right? So it's going to be 0.05 squared plus 0.05 squared, and then take the square root of that, right? And you should get SY equals something like 0.0707106, and then we can just put this number up here and round it off to the nearest number that is uncertain, which is 0.07. Just like that, okay? So all the prep work is done now. That's all considered prep work. That's all considered prep work, okay? So now we actually jump into figuring out some molarities. And I'm going to start on the next page so that I can have more room. But I might be switching back and forth to see, different numbers I've collected, okay? So let's go to the next page. The next step to do now, right, is that we have to figure out if one's not given to us, right, because presumably if you've already gotten your sodium hydroxide in the titration and you're already titrating the unknown acid, that means that you've already gone through and done the standardization using KHP. And presumably there should have been some kind of uncertainty that was associated with that, right? And so you would carry that number on. But in this particular question, there wasn't one. So you have to figure out the uncertainty yourself if one is not given to you. So how do you do that? Well, this is how you do it. The first thing we've got to figure out is what is the associated uncertainty with the number of moles, right, that has been transferred into the flask of unknown acid, right? Because remember when you're looking at this right here, right, in a titration here, I know I like to draw these over and over and over for you, but I'll keep on doing it so you guys get it, right? You have a number of moles of acid, and that's unknown, right? You don't know what it is, and you're doing this titration with a number of moles of base, right? But you know the number of moles of base because you have the concentration of the base, right? And so you have the concentration of the base, and then you have the initial and the final volumes, right? You can use that along with the concentration of the base, which is given up here as the 0.16266 molar, right? Use that along with the volume right here, which is 10 mils. You can figure out the number of moles that actually got transferred into the flask, right, and got it to its endpoint, right? So you can figure out the number of moles of acid there is. And so, since the problem didn't give you an uncertainty that was associated for this concentration right here of of standardized sodium hydroxide that's supposed to come from the KHP titration, you have to figure it out yourself, right? So, and for you to figure it out yourself, you've got to figure out the number of moles that actually got transferred into the base, right? So let's do that. So I'm going to start out by saying and writing this 0.16266 molar NaOH equals the number of moles of NaOH divided by the volume we had from the burette, which was on the previous slide right there, right, as being the 10 mils, right? So that would be 0.101 liters, okay? And that's going to give me the number of moles of NaOH. If I solve for this, and I just keep on saying that, but I want to make sure everybody's clear, right? And so my number of moles of NaOH is 0.0016266 moles of NaOH. Okay, and so now we have to convert this thing to number of grams, because I know generally during titrations we only use the number of moles of things to figure out the concentration of the unknown acid, but you don't have any kind of uncertainty associated with number of moles. You only have associated uncertainty when it comes to the individual elements that are on the periodic table, and so that's why you have to convert the entire formula to the number of grams that you actually transferred from the burette into the number of grams of sodium hydroxide that you transferred from the burette to the flask, right? So, the easy way to do this, the trick is that whenever you want to go from moles to grams, you just multiply by the molecular weight or the formula weight, right? If you want to go from grams to moles, then you divide by the molecular weight. And so this is a moles to grams, so easy as pie. Multiply the number of moles by the formula weight, which is 39.997, right? Grams per mole. Okay, and that's all you have to do there, because then you get the number of grams to be 0.065 grams of NaOH. So essentially, if you were to take that 10 mils of sodium hydroxide that you titrated into the flask, right? If you take that and that 10 mils and you evaporate it off all the water, the amount of grams of sodium hydroxide you'd be left with is 0.065 grams, right? And you have to do that. And the reason why you have to do that is because, again, we don't have an associated uncertainty with number of moles, right? Just like you don't have you don't know what a dozen, there's not an uncertainty with a dozen, right? Those are all exact numbers, right? A mole is also an exact number, so you need to have the only thing that was really measured here is the number of grams. And so the number of grams is what you apply your uncertainty to because of the uncertainties that you see that are on the periodic table in our textbook in the chart I gave you, right? So that's good. That's really good. And so what you can do now is go ahead and write out the number of moles, and then you can say in a way so that you can figure out what the number. You can calculate the number of moles based on the uncertainty that is associated with the number of grams. Okay, and so number of moles of NaOH equals, and it feels like you're going backwards and forwards, but we're just really writing all this out like individually so you know the steps. Okay, you take this number here, which is 0.065, right? And then it's going to be plus or minus the 0.003 grams. Okay. that's going to be divided by, I messed up there, my pen glitched on me again. Let me erase that and fix that. Okay, there we go. That's going to be divided by the molecular weight that we got ahead before with its uncertainty, which was right here, right? The 39 point, oops, sorry, yeah, that's it, 39.33, and its associated uncertainty. So 39.33, and that was 39.33. Where am I getting that from? Am I reading that right? Where did I get 39.33 from, guys? Oh, you know what it is? I have a math error here. See, got to go back and check on your math errors. Think about what you're doing, right? This actually should be 39.997,106, right? That's my apologies there. That's a math error. And then, so this number here should be actually 39.997. Okay. That's a math error. Sorry about that, guys. So yeah, I'm sure you guys did that math and saw that I did a math error there, a little math boo-boo, right? But yeah, so you probably got the 997. But see, the thing about it is, as you're going through these calculations, you can even see me as I'm going through the calculations. I'm typing them in the calculator just like you are. None of us are perfect, right? But as you're going through these calculations, you should be able to notice when things are like, that doesn't look right, right? And so think about what you're doing, and you should be able to catch it, right? So again, our sodium hydroxide, which is going to be the 39 point. I'll just erase that because the 33 is just going to confuse me. Here we go. Luckily, we didn't use that in any of our calculations yet. We're just now using it, so I caught the math error early. 997. There we go, right? 997 plus or minus the 0.003 grams per mole. Okay? Remember, that's how we figure out the number of moles of something. We take the number of grams and we divide it by the formula weight. And so again, just recall, right? I guess with this, the base that was used to make this, the sodium hydroxide that was used to make this sodium hydroxide solution was done on a balance that had an uncertainty, right, of 0.003, right? That's its uncertainty right there, right? Absolute uncertainty for the balance. Okay, which is interesting because in the previous one, right, we had a balance that was had an uncertainty of where did it go? Right here, 0.000002. So both times in both examples, right, we end up with an uncertainty from the balance, like the manufacturer of the balance, right, at 0.002 being the same uncertainty as what you get when you do the formula weight uncertainty, right? And we happen to get in this one too, where the balance, right, that was used to make this sodium hydroxide right here, okay? And I mean, I guess I forgot to put it in there, right? But the balance uncertainty here, or sorry, the uncertainty from the formula weight of sodium hydroxide 0.003 is the same as the balance that was used here, right? So same number again. So that's lucky us, I guess. But it doesn't matter. It could be anything, right? You look into the balance in your balance instruction manual and just look it up. Or again, uh, it's for you guys when you do the calculation in your lab report. You'll report the uncertainty of the balance from your uncertainty budget. Okay, that takes into account the human error, the absolute uncertainty that comes from the balance that was used. Right, that was used will stand in for an uncertainty if we don't have a true uncertainty that takes into account human error, right? So, but just a coincidence that this number is the same as this number, okay? And so you multiply this by divide this number by this number, and you get the number of moles, right? And then, since we have uncertainty associated, we can also calculate its uncertainty too, right? And so, just like in the previous example, right, we can do this by converting things into their relative uncertainties. So we already have the number of moles, which is right here. Okay, the number of moles is right here, right, that we calculated earlier. And so now we're just needing to calculate the uncertainty that is involved in the number of moles. Okay, so we'll convert it to the relative uncertainties. So at this point, convert to relative uncertainties. And so we'll do that by the same equation we've always been using. Sy over y equals the 0.003 for the uncertainty of the formula weight divided by the formula weight. They're 9.997. And that equals 7.5 times 10 to the negative 5. Or if you wanted to report it as an actual relative uncertainty, you can convert it to percentages, which that would be 0.0075%. But in calculations, we'll always use this number. Again, the reason for that is because for some reason the percent button, the calculator doesn't do anything right. So just keep the zeros in there. And then for the next one, yeah, so this is the relative uncertainty for the formula weight, right? Or I'll even do you a solid and put percent E here too, so that you remember that's what that means. And then we'll do the same thing now for the grams that we weighed, or the grams of sodium hydroxide, which is grams here, right? Again, percent E equals that. It's all the same. So 0.003 divided by the number of grams you have, and 0.065. That gives us then an uncertainty of 0.4, relative uncertainty of 0.4615. Or if you wanted to report that, that's about a 4% uncertainty, or even 5% actually. But yeah, it's like a 5% uncertainty. But it doesn't matter, right? Because we're going to be using this number right here for our calculation. Okay? Cool. So now let's see what the uncertainty is associated with the entire number of moles. So that's when we have to do our equation. So now percent E equals, Sy over y, square root of all the relative uncertainties, which is this one and this one, squared plus each other, square root, right? So we'll put it in there. Again, I like to use scientific notation of things and keep things short. 7.5 times 10 to the negative 5 squared times, plus the 0.04615 squared, right? And then so that should give you a relative uncertainty of 0.04615. Okay, cool. And so you might be thinking to yourself, that's like almost the exact same number, right? I shortened it up a little bit, but yeah, it's almost the exact same number. But the reason why is because you can see the order of magnitude difference here, right? There's a whole order of magnitude difference. This one here, the 4 6 is like, if you were to make a scientific notation, right? Move the decimal point over 2 times, that would be to the -2 if you had it in scientific notation. This one's a -5. So it's such a, the two uncertainties were so different from each other. You basically got the got the you basically got the biggest uncertainty as your biggest contributor here. And again, your biggest contributor here is actually the uncertainty that's involved in weighing things out, not the uncertainty involved in the very precise instruments they use to figure out atomic masses, right? You can even go to take this a step further, right? And if you wanted to, you could multiply this number right here. If you wanted to multiply this number by the mass that we had, which was no, sorry, not the mass, but the number of moles that we had right here, right? And that would give you the absolute uncertainty, right? And so if you did that, let me do some erasing here so it looks like mathematical operations, not arrows. I'm trying to get my pen to work again. There it goes. So all you have to do is solve for SY right here by plugging in the number of moles here, right, which is that number up there. And so you do that, multiply to get that 0.0016266, right? And then that equals that equals 0.00007, right? And so this would be your absolute uncertainty right here for a number of moles, right, of NaOH. Excuse me, but we don't need that, right? Not yet. When we're doing like a multiplication division, you want to do the easy route, not have to type in all your numbers into the calculator. So we'll just use this number here, which is the original calculation, which was before we try to solve for SY, the relative uncertainty here, the relative uncertainty. Oh man, it's Friday. So we'll use the relative uncertainty for all of our calculations going forward here. Again, you can do the absolute divided by the value, right, and do that too, which is the same thing as relative uncertainty, or you can just use the relative uncertainty that you just got, right, which is right here, right? So we'll use this for our calculations for the next parts. Okay. All right. So that's cool. So now all you have to do is do your regular old molar calculations, right? Your molar stoichiometry calculations, and just have uncertainties in there. So we'll write it out over here. We have our number of moles of sodium hydroxide, which is 0.0016266 moles of NaOH. And I already screwed up because I forgot to put in the uncertainty. So let's put that in first, because can't we forget that's what we're doing this for. So parentheses plus or minus, and the uncertainty we use will be this one right here, the one that we just calculated right here, right? The one that we just calculated. So plus or minus 0.04615, and that's moles of NaOH. Okay. For every 1 mole of NaOH, you have 1 mole of hydrochloric acid, right? So remember that whenever you have equivalencies, like 1 mole per 1 mole or something like that, of there's no uncertainty there, right? Because those are exact numbers. Okay. And then also take note, it is a 1-to-1 molar ratio, right? Based on our previous chemical equation that we wrote out right here, right? But just recall, or just not recall, but just keep in mind that it might not always be a 1-to-1 molar ratio. And so you can't just use M1, V1, M2, V2. In fact, don't do that at all because I'll just count it off. I'll just count it wrong, right? So do it correctly, okay? All right, so after that, right, we have moles of HCl now. That's great because that's what we needed to get to the thing, right? And so we have that already, thank God. So we did it previously here. Okay, so that was, if we look at the previous slide, we have the right here, right? This is the formula weight for hydrochloric acid, right? The 36.461. But interestingly enough, remember though, what we calculated here was actually a relative, it was an absolute uncertainty right there, right? And our calculation's in relative uncertainty. So what do we need to do to get that number to become a relative uncertainty? I'm asking you like you're in the room with me or something, but you're not. Just the same way we do all of them, right? All we have to do is do the division thing, okay? Do the division thing. And so, let's see here. Do I have room to do it over here? I think I do. Okay, so it'll be 0.002 divided by 36.461, right? And then that should give you the relative uncertainty, right? The SY over Y. Okay, and I'm just going to do it real quick in the calculator. 0.002 divided by 36.461. Okay, and the number I got is, I'm going to change it to scientific notation so it's easy to write. The number I got is this, 5.48 531. Yes, that sounds good. Times 10 to the -5. Right? So that's going to be our relative uncertainty, right, for this HCl formula weight uncertainty. Right? Also known as the percent E. Right? So that's the number that we'll use in our calculation on the next page. There we go. And so that's going to be, I already forgot what the numbers were. Good thing I wrote them down. 36.461, parentheses plus or minus 5.48 531. Is that the right number I had previously? Yes. Times 10 to the -5. Right? Grams of HCl. And that's all over 1 mole of HCl. And remember, normally what we would do is we would go straight to moles of HCl. And when we did that, when we go to moles of HCl, we could just divide by the volume. But remember, if you want to get the uncertainty with the HCl, you have to go to the number of grams first. I keep on saying that, but I just want you to remember. Okay. All right, so we have HCl there, 1 mole of HCl, and we'll do that calculation, right? For the number of grams, what you should get is 0.059307 grams of HCl. And then to get the uncertainty, what kind of operation do we have going on here? It's a multiplication operation, right? And it's a multiplication operation with relative uncertainties. Woohoo! So literally all we do now is go SY over Y, or also known as %E. I keep on doing that for you so you remember that they're the same thing, right? Equals the square root of the relative uncertainties, with a 0.04615 squared plus the 5.48531 times 10 to the negative 5 squared. And that gives you the relative uncertainty, which is 0.04615. Pretty much the same number again, because our biggest uncertainty is when we measure something out on a balance or with a volume on a volumetric flask or a burette, right? So that's where the most of it is. Okay. Good. So now we have the relative uncertainty of the number of grams, right? And so what we can do now is go back to converting that back to concentration, right? And so here we can then say the concentration. Maybe I should move over a little bit, sorry. The concentration of HCl, all right, with the brackets, equals the mass of HCl that was in the flask, which is calculated to be 0.059307, plus or minus the relative uncertainty that we just calculated, 0.04615, right? All of that is divided by, to get back to number of moles, is divided by the molecular weight, which is the 30, I already forgot what it was, 39, 36? Oh, there it is. For hydrochloric acid would be 36. The molecular weight of hydrochloric acid is 36.461, plus or minus its relative uncertainty that we had before, 5.48531 times 10 to the negative 5, right? All that is divided by the volume we had originally, right, at the very beginning of the equation, which was, where's that? Right here. 25 mils of hydrochloric acid, unknown concentration, and its uncertainty right there too, right? We needed to convert to liters though, so when we convert that to liters, it's going to be 0.025 plus or minus. So at this point, we need to figure out the relative uncertainty for the 25 mils that we measured of the hydrochloric acid unknown concentration out of the graduated cylinder, right? And so how do we do that? The same way we've done everything else. We'll go back to the problem, and the problem said here the uncertainty in the graduated cylinder is right there, which is 0.5 plus or minus. And so changing that to relative uncertainty is easy as pi. Remember, relative uncertainty or percent uncertainty here equals SY over Y. and that equals then the 0.5 divided by the 25, right? And when you do that, you should get 0.02, or if you wanted to report that somewhere, right, you could say it's 2% uncertainty on a graduate weight cylinder, which is kind of big, but you knew that. That's why you're not supposed to use graduate cylinders all the time to measure out very precise things. But again, we're going to be using this number right here, not the percent number in our calculation, because the calculator doesn't use the percent sign right? So we'll go back over here and we'll fill in this part right here to be 0.02, right? And so now we have our equation there, all in relative uncertainties, right? And so you could go ahead and do the molarity that you have for the HCl, right? So I'll go ahead and do that, and I think I'm going to be blocking that, so I'm going to go ahead and take my head away real quick, because I ran out of space here. Let me change over to just seeing the screen. There we go. So here we go, HCl concentration is then going to be just the numbers, not the uncertainties, right? Calculate that real quick, and I get, if I divide the 0.059307 divided by 36.461, and then divide that by the 0.025, the number I get is 0.0650 molar, right? But I'm going to leave a space over here so I can add in the uncertainty, right? And so how do I figure out the uncertainty now, right? Well, we have all those together, okay? We've done the calculation already to get the value of y right here. So now we just got to figure out the value of SY, or the absolute uncertainty, and we can do that from the relative uncertainties. And since this is a division operation, we'll do the percent E equals SY over Y. And you don't have to write that every single time. I'm just doing it so you remember that they're the same thing, right? Equals the square root, right, of the 0.0461 5 squared plus the 5.48531 times 10 to the negative 5 squared plus, and I ran out of room, so I'll go down here. It's a really easy number to write, which is 0.002 compared to the rest of them. Oh, sorry, one too many twos there. Or one too many zeros. Let me fix that. Got a little ahead of myself there. There we go. 2 squared, right? And so when we do that, when we get that, we get that equals to 0.050297. Okay, so that's our relative uncertainty. Okay, but again, I don't want you to report anything in relative uncertainty. I want you to report it in absolute uncertainty. So how do we convert it to absolute uncertainty? We do the SY over Y thing again. And then in the Y, we put in our concentration that we got from up here, right? So 0.0650, like so, okay? And then we solve for SY, and turns out that SY, or the absolute uncertainty, is equal to 0.003. Well, that's good, because now we see that the uncertainty, I think it's actually a lot longer than that, but the first digit after the decimal point is the 3. That's not a 0, so we'll end it at the 3, and then we'll put it up here into parentheses as plus or minus 0.003, right? And then we know that if the digits and the uncertainty are only 3 digits behind the decimal point, that means we can just get rid of this last zero right here, right? And so your answer then would be, I'm gonna move it over here just so you can see it, right? And your final answer is this: concentration of HCl from this calculation, from this titration, is 0.065 plus or minus, forgot the parentheses, but plus or minus 0.003. Right? Molar, right? And just like in high school and everywhere else in math, you can just square it, put a box around it so you know where the answer is. Okay? And that's how you calculate an uncertainty for molarity from a titration calculation, right? So this is what I expect you to do on the lab report for all your trials that you did in your titration lab, and then make sure you know how to do this, right? Because your exam is coming up on Monday, and it's going to be one question, right? And it could be any kind of things like this where we try to figure out where I ask you to figure out the concentration of something plus its uncertainty, and it could be like this from a titration. It could be like it from just straight up weighing something and dissolving it in something, right? And so just remember to study this and to study that, and then from weighing something and from a titration. But then also remember your statistical tests too, like the F test, the T test, and then the Grubbs test. And you should be good to go for the test on Monday, and also for your lab. If you have any questions, let me know, and I'll see you on Monday.